If you remember, in grade 1, you learned to add scalars. Your teacher didn't tell you you were adding scalars, but that's what you were doing. 1 plus 2 was equal to 3. In grade 6, you learned to add vectors, but vectors in one dimension. Maybe it was 1 to the east, 2 to the west. That would give you -1. 1 plus -2 gives you -1, or 1 to the west. Or it could be 1 to the east plus 2 to the east gives you 3 to the east. You may not have called it adding vectors, but that's in effect what you were doing, was adding vectors in one dimension. Now we're learning to add vectors in 2 dimensions. What if we have 1 to the east and then 1 to the south, or 3 to the west and 4 to the north? How do we add those vectors together? We're going to use skills that we've learned previous to this in math class, but we're going to put it together to actually accomplish the vector addition for the first time today. Before we do that, I want to remind you of our reference frame. That's important because we're going to ultimately end up solving for components of a vector as a tool to add the vectors together. So we have to know what our x component and our y component is. Just a reminder from yesterday that anything horizontal is going to be an x component. It's an x-axis or an x component. Anything vertical is going to be a y component. There is also a z component or a z-axis, but we're not going to deal with that. That's the one that comes out of the page and into the page. And we're going to deal with 2-dimensional problems where we have x and y, not 3-dimensional problems where we have x, y, and z. Although the analysis wouldn't be that much harder, we don't have to do it. Now, we can find the x and y components of certain vectors. We're going to have to do that. We're going to have to find the x and y components of certain vectors in order to add them together. Before we actually calculate or determine the values of x and y, I want to make sure that we can determine what is x and what is y first. So we're going to look at the first example that's in your notes on this, example number 13, and not try to determine what the values of x and y components are, but just simply label the x and y components. First of all, in the first question, that 10 meters, whatever the number is, that is x component. Remember, anything horizontal was x, anything vertical was y. So there is no y component for the first one. There is no x component for the second one. If I want to label the next one as x and y, this one would be what? This one would be x, and this one would be y. So if I can find the value of that side of that triangle, then I've found the x component of 10. If I can find the value of this side of the triangle, then I've found the y component of 10. We'll worry about how exactly we find those values in a few moments. Next one. Which component would this be right here, x or y? This would be the y component. This one would be the x component. This would be the x component. This would be the y component. This would be the y component. This would be the x component. Good. That's the first step. Knowing which is x and which is y is the first step. Doesn't do you any good to be able to calculate these sides of the triangles if you don't know which one is x and which one is y. That's the first step. Now comes the second step, and actually determine those values. This one's easy, right? The x component of this one is 10, and the y component of this one is 0. The x component of this one is 0, and the y component is 7, right? These ones are a little bit harder. In order to get these ones where we have these angles, we have to be familiar with our trig functions. I'm going to review those with you. Some of you are very familiar with them from Math 10, maybe second semester last year. Some of you are less familiar with them depending upon which class you were in and depending upon whether you took math first semester or second semester last year. There's a little saying that helps us to remember which trig function is which. Most of you will probably remember SOHCAHTOA. SOHCAHTOA. These three little mnemonic devices remind us which sides of a triangle we use with which trig function. I'm going to draw a triangle right now. We'll make it a right-angled triangle. By the way, we can only use these when we have a right-angled triangle. I'm going to label an angle right here, theta. Which side of this triangle is there's three sides, remember, opposite, adjacent, hypotenuse. Which side of this triangle is the hypotenuse? You know, which side is the hypotenuse? Good, across from the right angle. The hypotenuse in a right-angled triangle will always be the longest side, and it's always across from the right angle. So this is going to be the hypotenuse every single time. Now, which one's the adjacent? Look. Yeah, this is the adjacent. There's two sides that always touch the angle. Here's the angle, two sides always touch it. Always the adjacent, always the hypotenuse. Well, the hypotenuse is the long one, so the adjacent has got to be the short one. Does that make sense? There's a long side and a short side that touch the angle. The long side is the hypotenuse. The short side is the adjacent. The one that's opposite to the angle, or in other words, the one that's not touching the angle, is the opposite side. Now, there's four variables there. Every question you get involving trigonometry is going to involve three of those variables. Theta, opposite, adjacent, theta, opposite, hypotenuse, theta, adjacent, hypotenuse, so on. Three of those four variables. You've got to decide which variables are relevant and then decide which trig function you're going to use along with it in order to solve for a particular side or in order to solve for an angle. Now, let's go back to those same vectors that we had drawn, but this time use our trig functions, our SOHCAHTOA, in order to actually find the components. First two, as we said, were pretty straightforward, pretty easy. The x component of this one is 10. The y component is 0. The x component of this one is 0, and the y component is 7. All of it's y component, none of it is x component. But what about the next one? I don't even see a triangle here. We've got to turn this into a triangle. What I want to do is draw the triangle around the angle. Don't draw like this, because now the angle's outside the triangle. Right? Draw it like this, so that the angle is inside the triangle. Label this one, what is it? This one is labeled x, this one is labeled y, right? 10 meters, what is that? Opposite, adjacent, or hypotenuse? Hypotenuse, yeah. I want to find the x side. What side of the triangle is the x side? Opposite, adjacent, or hypotenuse? It's adjacent, right? It's touching the angle, but it's not the long side, the hypotenuse, so it's the adjacent side. We're going to say which trig function goes with adjacent and hypotenuse. What is it? Cosine. So let's say cosine 30 degrees is equal to adjacent over hypotenuse. X ends up being equal to 8.66 meters. I'll show you that on the calculator. Make sure that you can get this. Say 10 times cosine 30, the 10 goes up by multiplying. 10 times cos 30 gives me 8.66. Now for the y component, which side of the triangle is the y component? Opposite, adjacent, or hypotenuse? Aoife? Opposite. So opposite and hypotenuse go with sine function. Yeah, so we're going to say sine 30 degrees is equal to opposite over hypotenuse. Y ends up being equal to 5.0 meters. We're not adding vectors yet. I told you earlier we were going to add vectors today. We are going to add vectors. This is just learning the tools. You go to construction class, you don't build a table on your first day. You learn how to use the tools. That's what we're doing right now, is learning the tools, or at least reviewing the tools. And then a little bit later on today, we'll actually learn to use those tools to add the vectors together. Okay, next one. 7 meters at 50 degrees. 7 meters at 50 degrees. Draw a triangle. Don't draw the triangle here because the angle is outside the triangle. Draw it such that the angle is inside the triangle. It looks like this. Which side is x? This one or this one? Position 1 or position 2? Which one's x? The bottom one. This is y then. Which side of the triangle is x? Opposite, adjacent, or hypotenuse? It's adjacent. It's the one that's beside the angle, but not the long one beside the angle, because that's the hypotenuse. If I have adjacent, or if I'm looking for adjacent and I have hypotenuse, which trig function goes with adjacent and hypotenuse? So, ka, toba. It's cosine, right? We're going to say cosine 50 degrees is equal to adjacent over hypotenuse. X ends up being equal to 7 cosine 50. And 7 cosine 50 is 4.4995, or we'll just say 4.5. Now, the y component, well, the y component is the opposite side, opposite hypotenuse, sine theta is equal to opposite over hypotenuse. The y component is 7 sine 50. And that gives me 5.36. So how much of that 7 meters is x? 4.5. How much of that 7 meters is y? 5.36. Easy when we look at this question to see how much is x and how much is y. A little bit harder here, but we've done it. Okay? 4.5 is x and 5.36 is y. Let's do the next one. Draw your triangle. This is x. This is y. 5 meters. Is that opposite, adjacent, or hypotenuse? Turn opposite, adjacent, or hypotenuse there. 5 meters. Hypotenuse, yeah. X side of the triangle. X side of the triangle, is that opposite, adjacent, or hypotenuse? Not hypotenuse, because we just determined that the other one is, right? X, opposite or adjacent, Dylan? That's going to be opposite, yes. So far, x has been adjacent, right? This time it's opposite. Opposite and hypotenuse go with sine. So let's say sine 35 degrees is equal to opposite over hypotenuse. X is 5.0 sine 35, and 5 sine 35 is 2.87. We're going to say cosine 35 is equal to adjacent over hypotenuse, or y over 5.0. 5.0 cos 35 gives me 4.10. How much of that 5 meters is x? 2.87. How much of that 5 meters is y component? 4.1. Harder than if it's just horizontal or vertical, but we're getting it, right? Using sine cos, we can determine how much of that 5 meters is x and y. Last one for now. Draw a triangle right here. Make sure the angle is inside the triangle. Label this as x, label this as y. Which side of the triangle is x? Which side of the triangle is x? Opposite, adjacent, or hypotenuse? It's, no, not the adjacent. Opposite, it's opposite, yes, it's opposite. This is the hypotenuse, 20 is the hypotenuse, it's the longest side. The adjacent side is the other one that's touching the angle. This isn't touching the angle at all, so it's got to be the opposite side. Opposite and hypotenuse go with sine, cos, or tan. Opposite and hypotenuse. Ethan, opposite and hypotenuse go with what? Right. So we're going to say sine 60 degrees is equal to opposite over hypotenuse. X is going to be equal to 20 sine 60, which I believe is 17.32. 17, I want to say, what is it? 17.32, yeah. Now, I want to find the y component. The y component is the opposite, adjacent, or hypotenuse? Yeah, it's the adjacent. It's the one that's touching the angle, but not the long one. It's the adjacent. We have the hypotenuse, so we're going to say cosine 60 degrees is equal to adjacent over hypotenuse. Take the 20 up by multiplying. 20 cos 60 gives me exactly 10 meters. So how much of that 20 meters is x? 17.32. How much of that 20 meters is y? 10 33.0 meters. Make sense? All right, I'm going to ask you to take a look at worksheet number 6 right now. Worksheet number 6. There's 8 questions on that page. The first 3 of them are very straightforward, just those straight horizontal or vertical lines. And then the next 5 require you to use sine, cos, or tan in order to determine the x and y components. I want you to find the x and y of all of them, and that's it. You're not adding vectors together. You're just learning to use the tool. Once we've mastered that, we'll move on to actually adding our vectors together. Let's have a look at number 7 here, guys. It says we got a vector 40 meters. We want to find the x and y components of this. We're going to label x and y first. Draw the triangle around the angle. This is x, this is y. Which side of the triangle is our 40 meters? Is that opposite, adjacent, or hypotenuse? That's the hypotenuse, right? Now, x is which side is that, opposite or adjacent? It's the adjacent side. So which trig function goes with adjacent and hypotenuse? Going to be cosine. So let's say cosine, Parker. Cosine 30 degrees is equal to adjacent over the hypotenuse. X ends up being equal to 40 times cos 30, which I believe works out to be 34 point, what is it? 34.6 meters. There's my x component. Now, my y component is the opposite side of the triangle. I have the hypotenuse, so opposite with hypotenuse is sine function. To find the y component, we'll say sine 30 degrees is equal to opposite y over hypotenuse. Y is equal to 40 times sine 30, which ends up giving me 20 meters. So x component, y component. How much of that 40 is x? 34.6. How much of that 40 is y? 20 meters is y. Got it? Yep. Yeah, that's a good question. It's going to be yes. Yeah. The question, if you didn't hear that, was should that 20 be negative 20? Right now, it doesn't really matter whether you call it negative or positive. When you go to add the vectors together, yes, it's going to become negative, but we'll deal with that when the time comes. You want to call it negative now because it's downward? That's fine. Eventually, you're going to have to do that anyways. I just wasn't going to deal with that quite yet. All right. Let's move on. We've got the tools. Now it's time to actually start adding vectors together with the tools that we've learned here. Here's the first example that appears in your notes here. We've got 200 meters, 100 meters, and 75 meters. We want to add these vectors together. Look, if they were all to the right, this would be easy. 200 plus 100 plus 75 is 375. If 2 of them were to the right and 1 was to the left, it would still be pretty easy. We just add them together, making one of them negative value. But because there's a 200 to the east, a 75 to the west, and a 100 to the south, it becomes a little bit trickier. You now know all of the math required to do this. We've just got to put it all together to actually solve it. What's the x component of that 200 meters? How much of that 200 meters is horizontal? All of it, 200 meters. So let's fill that in. The x component of the first displacement should be delta d with the arrow, by the way, is 200 meters. What's the x component of d2? What is it? 0, right? Because that 100 meters is all y component. It's all downwards. Does that make sense? What's the x component of the 75? Now it becomes important. What's the x component of the 75? Negative 75. Negative because it's going to the left. So I'm going to fill in here negative 75. Amelia?
Will there always be arrows?
Yes. Yes, there will always be arrows on it, yeah. If you just saw the line 75, there's no way for you to determine whether that's right or left, right? There is no direction with it. If you have a vector, there has to be a direction indicated. And if it's a vector diagram, that direction is always indicated by the arrow on the line segment. Okay, let's add these up. Let's get the sum of all the x components here. 200 plus 0 plus negative 75 gives me 125 meters. So I found all my x components, and then I added up all my x components to give me 125. Now let's do the y components. How much of this first vector, 200 meters to the east, is y component? What is it? 0. Yeah, it's all horizontal. How much of that 100 meters is y component? 100? Negative 100, because it's going downward, right? We have to pay attention to the direction here now. It's negative 100. How much of that third one is y component? How much is it? Good. 0. Yeah, it's all x component, right? So we're going to say 0 plus negative 100 plus 0 to give me the sum of the y components ends up giving me negative 100 meters. We're still not done, but we're getting there. Now what I want to do, and pay really close attention to this, now what I want to do is draw a new vector diagram. This is a vector diagram. Vector diagrams must be drawn what we call head to tail. The head of one vector is drawn next to the tail of another vector. Make sense? Except the resultant. The resultant vector, which we give the symbol r to, is not drawn from head to tail. The resultant vector is drawn from start to finish. So we're saying 200 head to tail, 100 head to tail, 75 head to tail, but then the resultant vector is drawn from start to finish. The resultant vector is the sum of all the vectors. Think about that. When I added 3 to the east plus 5 to the west, the resultant vector was 3 plus negative 5, which is negative 2. My resultant vector here is the sum of the vectors as well, except it's just not quite as easy to find as 3 plus negative 5. Okay, so let's redraw this now. Let's draw a new vector diagram. The first vector that we're going to draw is 125. It's positive 125, and it's to the right. How did I know that 125 is to the right? It's the x component, and it's positive. Now, the next one, the 100 meters here, we're going to draw that like this. How did I know to draw that on the y-axis? Because it's the y component. How did I know to make it negative? Oh, sorry, I just gave it away. How did I know to draw it downward? Because it's negative, right? Yeah, go ahead. Yeah, that would be okay, although I'd avoid it because you generally want to avoid putting those into your trig functions, your negative values into your trig functions. But if you wrote it down, I wouldn't mark that wrong. No, I wouldn't. Notice, guys, these are drawn head to tail, right? The head of the blue vector to the tail of the green vector. Now, my resultant, look at that resultant. Doesn't that look a lot like this resultant? If I had have drawn it to the same scale, it should look exactly the same. But now it's easier to find because I have a nice right-angled triangle. How do you find the value of r there? Yeah. Yes. A, B, C. We could say a squared plus b squared is equal to c squared. Now, we're not usually going to say it like that, but that's exactly what it ends up being. If c squared is equal to a squared plus b squared, then c would be the square root of that. We're usually going to say, rather than c is equal to the square root of a squared plus b squared, we're usually just going to say r is equal to the square root of whatever the numbers are squared. But it ends up being the same thing, right? It is the Pythagorean theorem. It's just a matter of what you call it. So the c, we're calling it r. Now, let's do this on our calculator to make sure that we can all get the value of r there. If we try to do it in one step, we'll say second function square root, then let's say 125 squared plus 100 squared, and then let's end the bracket. Looks like this. we should get a value of r of 160, which we technically round to 2 digits because of that 75. So 160 ends up being 1.6 times 10 to the 2 meters. So we're saying 200 plus 100 plus 75 is equal to 1.6 times 10 to the 2. Because we're adding vectors in different dimensions. Which, by the way, 200 plus 100 plus 75 is the same thing as saying 125 plus 100, just a different way. We're not quite done, though. What are we missing from this? What are we missing from this resultant vector, the sum of these vectors? What are we missing? Direction. Yeah. The only way that we can find direction here is by finding an angle. The angle is always measured at the start of my vector diagram, where my resultant vector starts. So don't put it down here because that's at the finish. Don't put it here because it's in the middle. Draw it at the start. Now, I've got clearly labeled on that new vector diagram, that right-angled triangle vector diagram, I've clearly got labeled 2 sides. They are the, which sides? 125 is the adjacent, 100 is the opposite. Which trig function goes with opposite and adjacent? Tan. So let's say tan theta is equal to opposite over adjacent. Now, let's rearrange the solve for theta. It's the inverse tan, or second function tan, of 100 over 125. Now, follow along with me on my calculator here again. Second function tan of 100 divided by 125 gives me 38.6 degrees, or we'll make it 39 degrees. That's the direction, right? Oh, I'm still not quite done, but I am ever so close. 39 degrees relative to what? Clockwise, counterclockwise? What? Like, how do we express this? I'm going to draw my x and y axis here. My east and my south, right at the start of my diagram. This angle is measured from the east. Would you agree with that? But yet it's going south from the east. Agree? South from east. We're going to express that south from the east. We're going to express it as south of east. So we're going to say this is 1.6 times 10 to the 2 meters at 39 degrees south from east, or south of east. Now, I'm not going to solve this any other way, but I do want to show you one thing that maybe some of you are wondering about. Before I show you that, though, I'm going to ask a question. 5 to the east plus 2 to the west is what? Plus 5. 5 plus negative 2 is 3. Okay. 5 plus negative 2 is 3. What about negative 2 plus 5? It is 3. Did it matter what order I added those vectors in? No, it didn't. Doesn't matter what order I add these in either. Okay, I could have said, instead of 125 and 100, I could have said 100 and 125. Those are still drawn head to tail, right? Does that make sense? My resultant vector would have been this, and when I calculate that, I would have got it to be 1.6 times 10 to the 2. The only difference here is my angle would not have been 39 degrees. My angle would have been 51 degrees. How can that be right? Well, it's not 51 degrees south of east. Rather, where is that angle measured from? From the south. So I'm going east from south. So we would call this 51 degrees east of south. That's the same answer. Okay, that's the same answer. South of east, 39 degrees south of east, 51 degrees east of south, exactly the same answer. It's like saying, where are you right now, Mr. Dickie? Okay, I'm 2 meters from the front of the room. I'm 7 meters from the back of the room. Don't they both show me the same thing? 2 meters from the front, 7 meters from the back of the room? Okay, it's just a different reference frame. You do not need to do it both ways. This way, the way that we originally did it, is correct. But so's this. This is correct as well, as long as you follow those rules of vector diagrams and vector addition. Our homework for tomorrow, of course, is quiz number 6, which is on velocity versus time graphs. But we also now have worksheet number 6. I want you to do, worksheet number 7. Worksheet number 7, and I want you to do questions 1 to 6.